The paper discusses the characterization of multiplicative asterisk operator Jordan-type maps on alternative algebras. It starts by introducing the concept of multiplicative asterisk operator Jordan-type maps, which are a class of maps that generalize the notion of asterisk operator ring isomorphisms. The authors then proceed to study these maps in the context of alternative algebras, focusing on their properties and behavior. They provide several key results, including propositions that establish the properties of the maps under certain conditions. The paper also discusses the importance of these maps in the study of non-associative algebraic structures, highlighting their role in characterizing isomorphisms between alternative algebras. Throughout, the authors use technical terms and mathematical concepts specific to the field, ensuring the accuracy and precision required for expert researchers and stakeholders. Here is a combined summary of pages 3 and 4. The main theorem of this paper is presented, which states that if A and A are two alternative asterisk operator algebras with identities Ia and 1A, respectively, and E1 and E2 are non-trivial symmetric idempotents in A, then a bijective unital map phi, a right-pointing arrow A, that satisfies certain conditions is asterisk operator additive. The conditions include phi, Qn asterisk operator, xi, A, B, equals Qn asterisk operator, phi, xi, phi, A, phi, B, for all A, B element of A and xi element of 1A, E1, E2. To prove the asterisk operator additivity of phi, three lemmas are presented. Lemma 2.1 shows that phi, 0, equals 0, which is a straightforward consequence of the surjectivity of phi. Lemma 2.2 proves that phi, A11 plus B22, equals phi, A11, plus phi, B22, for any A11 element of A11 and B22 element of A22, using the injectivity of phi and proposition 1.2. Lemma 2.3 demonstrates that phi, A12 plus B21, equals phi, A12, plus phi, B21, for any A12 element of A12 and B21 element of A21, again using the injectivity of phi and proposition 1.2. The proof of lemma 2.3 involves a series of calculations using the definitions of Qn asterisk operator and the properties of phi. It is shown that T11 equals T22 equals 0 and T21 equals B21, where T is an element of A such that phi, T, equals phi, A12, plus phi, B21. The proof also uses the fact that phi is injective in the properties of the idempotents E1 and E2. Finally, lemma 2.4 is stated, which asserts that phi, A11 plus B12 plus C21, equals phi, A11, plus phi, B12, plus phi, C21, and phi, B12 plus C21 plus D22, equals phi, B12, plus phi, C21, plus phi, D22, for any A11 element of A11, B12 element of A12, C21 element of A21, and D22 element of A22. The proof of lemma 2.4 is similar to that of lemma 2.3 and is omitted. The main theorem follows from these lemmas. By injectivity of phi, we have the identity Qn asterisk operator, E2, T, equals Qn asterisk operator, E2, B12, plus Qn asterisk operator, E2, C21, which implies T22 equals 0, T12 equals B12, and T21 equals C21. Similarly, using Qn asterisk operator, E1, T, we obtain T11 equals A11. This leads to the conclusion that phi, A11 plus B12 plus C21 plus D22, equals phi, A11, plus phi, B12, plus phi, C21, plus phi, D22. Furthermore, lemmas 2.6 and 2.7 demonstrate that phi, Aij plus Bij, equals phi, Aij, plus phi, Bij, for all I, j. Lastly, lemma 2.8 shows that phi, I plus bii equals phi I plus phi bii for I equals 1, 2. These results collectively highlight the injectivity and surjectivity of phi, establishing a foundation for the subsequent proofs and analyses in the paper. The research paper discusses the properties of alternative asterisk operator algebras and their isomorphisms. It begins by presenting a theorem on the additive nature of a function phi, which is crucial for understanding the asterisk operator ring isomorphism. The authors then delve into the specifics of when phi is a asterisk operator ring isomorphism, introducing conditions such as the existence of non-trivial symmetric idempotents. They also discuss the implications of these conditions on the properties of phi, including its behavior with respect to addition and multiplication. The paper concludes by examining the behavior of phi under various transformations, including those involving idempotents and alternative algebra operations. Throughout, the authors employ mathematical equations and lemmas to support their arguments, providing a comprehensive analysis of the topic. The paper discusses the concept of a new product on a ring with involution, which is a non-associative and non-commutative generalization of the usual product in a ring. This new product, denoted as A, B, equals AB plus BA, is used to define a ring, a non-associative and non-commutative ring with involution. The authors also introduce the notion of a Liud-Jordan type map, a map that preserves the new product and satisfies certain conditions related to the involution. The main result of the paper is Theorem 2.1, which states that if A and A are two alternative factors, then any Liud-Jordan type map between them is an additive ring isomorphism. This theorem is proven by showing that the map preserves the new product and the involution, and then using these properties to establish additivity. In the application section, the authors apply their results to alternative algebras and wifactors. They show that any Liud-Jordan type map between two alternative wifactors is an additive ring isomorphism, and that any nonlinear Jordan type map between two alternative wifactors is also an additive ring isomorphism. The paper concludes with a list of references, which include various works on non-associative normed algebras, alternative rings with involution, and maps preserving Jordan triple products on algebras. The authors' contributions are summarized as providing a new perspective on the study of Liud-Jordan type maps and their relationship with additive ring isomorphisms in the context of alternative factors.